Let's jump right into it. Today, in this explainer, we're diving into the absolute beating heart of offshore power systems. I'm talking about gas turbine-driven generators. If you're an electrical engineer working in oil and gas, understanding the raw mechanics and the precise electrical control of this machinery, it isn't just a nice-to-have, it's an absolute necessity. So picture this. You're standing on the vibrating deck of an FPSO, a floating production, storage, and offloading vessel out in the Gulf of Mexico. It's 2 a.m. The ambient temperature is a stifling 35 degrees Celsius, and the humidity is sitting at practically 100%. Beneath your feet, you can feel this rhythmic, powerful vibration. That's the harsh reality of our equipment. It's a massive machine spinning at 3,000 RPM in the middle of a brutal environment. It's relentless, and honestly, it's pretty fascinating. Here's the roadmap for what we'll be covering today. We're going to start with the offshore beating heart, then break down the Joule cycle, compare textbook specs against the harsh reality, dive into speed governing and droop, and finally, wrap up with commissioning and maintenance. All right, part 1, the offshore beating heart. Think about it like this. This massive machine burns wellhead gas to produce every single watt of electricity on your platform. It's literally the undeniable lifeline of the entire operation. Without it, you've got no lights, no pumps, no drilling, no life support. It basically functions as a gas generator that directs high-velocity hot gas straight into a power turbine, which is directly coupled to your generator. So yeah, it is the alpha and omega of your isolated offshore grid. Moving right along to part 2, the Joule cycle explained. To really understand how this works, we need to look at the thermodynamic baseline. The gas turbine operates as a heat engine on the Joule cycle. You might also know it as the Brayton cycle. And it breaks down cleanly into 3 really visceral phases. First, you compress the incoming air. Second, you inject fuel and combust the mixture. And third, you expand that hot, high-pressure gas through the turbine blades to generate rotational mechanical energy. Grounding this in some engineering math for a second, air is drawn in at atmospheric pressure and compressed adiabatically, which just means it's compressed without losing any heat to the surrounding environment, right? This dramatically raises its temperature and reduces its volume. Just look at the sheer energy required to even prime the system. Looking at the compressor work equation, you can see you're forcing air into a tighter and tighter space, fighting thermodynamic resistance every single step of the way before combustion even happens. Now, here's a stat that always blows my mind. Roughly 50 to 60% of the gross turbine output goes right back into driving its own compressor, leaving only the remainder as net shaft output. Let that sink in. More than half of the explosive mechanical energy the turbine generates is instantly consumed just to keep the air intake pressurized. The electrical generator only gets to use what's left over. Which brings us to part 3, textbook specs versus harsh reality. You know how it is. Manufacturers give us this beautiful, pristine ISO baseline. 15 degrees Celsius, sea level, completely clean engines straight off the line. Sure, that looks great on paper. But when you take that machine and drop it into a tropical or desert environment with 35+ degree heat and salty, humid air, those textbook numbers just go right out the window. Because, as it turns out, gas turbines are incredibly sensitive to ambient air temperature. And this is exactly where the derating factor kicks in, and it's a huge deal. You have to derate the turbine's power output by 0.5 to 0.8% for every single degree Celsius above that 15-degree ISO standard. Just think about our offshore platform operating in 40-degree heat. You're 25 degrees above the baseline. Multiply that by an average 0.65% derating, and wow, you've suddenly lost over 16% of your total power generating capacity before you've even flipped a switch. But wait, it gets worse. As blades naturally erode and combustion deposits build up, you face a rule of thumb 5% power loss simply from operating what we call a dirty engine. Your lube oil gets less efficient, air filters clog up, and the aerodynamic efficiency of those turbine blades degrades over time. If you don't account for this 5% dirty engine penalty during the design phase, well, you're going to face some severe embarrassments and likely blackouts once the machine is actually in service. So how do we handle this? Let's get into part 4, speed governing and droop. How do we actually control this volatile, heat-sensitive beast to keep a stable power grid? We use droop governing. This is honestly the most reliable method for accurately sharing electrical load among multiple generators without causing cascade tripping. See, an ungoverned gas turbine has an incredibly steep, unstable speed-to-torque ratio. Droop governing introduces proportional control. It basically tells the engine, hey, as the electrical load gets heavier, just allow your mechanical speed to drop slightly. The key metric you need to know here is that a standard 4 to 5% drop in speed is expected when a 100% load is applied. For example, if your system runs at 50 Hz at no load, slapping a full electrical load on it will cause the frequency to naturally droop down to roughly 48 Hz. This predictable program sluggishness is exactly what lets two or more massive generators operate in parallel safely. They share the power demand without constantly fighting each other for control and tripping the whole platform offline. Finally, let's wrap up with Part 5, Commissioning and Maintenance Recap. Remember that heavy 5% dirty engine penalty we just talked about? Your absolute best defense against that is the routine compressor wash, scheduled every 500 to 1,000 hours. Seriously, this is non-negotiable for offshore survival. Further down the line, you're looking at comprehensive hot section inspections around 8,000 to 12,000 hours, and a massive, complete major overhaul when you hit that 25,000 to 50,000 hour mark. The harsh environment is constantly trying to destroy this machine. Maintenance is simply how we fight back. And of course, when you're initially bringing the system to life, you've got to rigorously march through this exact 5-step sequence to ensure absolute safety and grid stability. First, pre-commissioning checks like Megger testing insulation. Second, the first fire, which is a highly supervised ignition. Step 3 is synchronization, where you perfectly match voltage, frequency, and phase angle to the bus. Step 4 is incremental load testing. And finally, Step 5 validates your under-frequency and over-temperature protection relays. Skip even one of these steps, and you are risking a catastrophic plant failure. Just don't do it. All right, let's bring it all together. If you take away anything from this explainer today, memorize these 5 non-negotiable numbers for your field guide. First, turbine D rating. Expect a 0.5 to 0.8% power loss for every degree Celsius above ISO. Second, the dirty engine factor. Always account for a minus 5% power drop. Third, droop governing. The standard is 4 to 5%. Fourth, compressor wash. Mandated every 500 to 1,000 hours. And fifth, commissioning. Always follow the 5-step sequence. So, with our turbine spinning perfectly and our mechanical power finally governed, I want you to ask yourself something. How exactly do we translate that sheer mechanical brute force into the flawless alternating current our grid absolutely demands? Well, that is the magic of the synchronous machine, and that's exactly what we're going to tackle next time. Until then, keep questioning how the systems around you actually work.